we start with this. My old history teacher. It's so funny. I went to Great Lakes Adventist Academy, and they had this thing called Parents' Day. That the parents would come up and like sit in all your classes. Because, of course, it was a boarding school, so you'd go away. So the chance for them to meet your teachers, all that kind of stuff. So my history teacher, his name was Mr. Riker. He actually still teaches at Great Lakes. He's a good guy, good friend. He's not that old. Come on. I'm not that old. So, stay with me. Stay with me. We've only got 10 minutes here, guys. So for his history classes, which, don't tell Mr. Cooksey, but I always thought history was the boringest subject in the world. But this is what he would do. And I kid you not. It was really stupid, but this is what he did. He would say, okay, we're going to learn about history now, so we're going to go into a time machine. So I want you to close your eyes. So do it. Close your eyes, close your eyes, close your eyes. And then he would do something like this. Whoa, the time machine, whoa. And then you open your eyes, and here we are. We're back in whatever year we're going to. So, it's kind of goofy, Marlon, right? But that's what he did. So whenever I do this lesson, because we only have a few of these history pieces. Come back to me. There's only a few little history pieces like this where you have to know names and people who do stuff. But I always think about that when we do that. All right? So here we'll begin this thought with this history of the model of the atom. And remember our think tube, right? That a model is something that we use to talk about something we can't actually observe, right? Or maybe that we can observe it, but we can't actually just see it with our own eyes, and so we have to put this model together. So we've been thinking about stuff for thousands of years, about wondering how the world works. And back in the day, they would think that there was really kind of these four things. Things were either hot, or they were cold, they were wet, or they were dry. And it makes sense. You and I, we don't deal with weather every day, right? We're inside most of the time. But if you've been camping, if you've been camping for a long time, let's say you camp for a week or more, you become very attuned to how cold or how hot or how wet or how dry things are. And if you're out camping for a week and it rains the whole time, life is tough, right? So that's what they kind of put things in that category. Now, way back in the day, this guy named Democritus, he said, you know what? I think that there are these small, indestructible, indivisible things that make up everything else, and I want to call them an atom. It's a Greek word, right? Yeah. And everything else is just empty space. If there's something that doesn't have these atoms present, it's just empty space. And everybody back in the day thought this guy was crazy. There was a better philosopher, or I should say a more well-known philosopher by the name of Aristotle, who said, no, everything is these elements, these four things, fire and wind and earth and water. And everything is made up of some combination of those four pieces, right? And again, because Aristotle was such a progressive, influential philosopher, that was what we believed, really, for 2,000 years that lasted. When Jesus was here, that's what he would have thought. Well, he would have known, because he was the creator, but his contemporaries would have thought that same piece. Okay? And again, he said there was no such thing as empty space. Empty space is always filled with something, right? Even the air around you, there's stuff in it. That's what wind is, right? Are you with me? So then we started rolling into about the 1800s when this kind of scientific revolution happened. And we start off with this Englishman by the name of John Dalton. And what's cool about him is he was the first guy that said, you know what? That Democritus guy, he was right. There is actually some things that we're going to call atoms, and that matter is made up of them. And these are indivisible, indestructible little particles. Everything in the world is composed of these elements, of these atoms. And if I take gold, all the atoms in that gold are all the same. But if I have some silver, all the atoms in that silver are different than the atoms in gold. Now again, you guys go, well, duh, but this was a fairly important thing to say, hey, there's actually a difference between those things, between gold and silver. They're not just different combinations of fire and earth, or wind and water, right? He also said that atoms combine to form reactions in simple whole number ratios. All these things are very true. Like that second piece, all atoms of an element are the same, and atoms combine, we still believe that. Over 200 years later, that's still like the foundation of our atomic theory. Do we believe the first sentence, that atoms are indestructible and indivisible? They can't be smaller? No. No, there's pieces we know that are smaller than that. We'll talk about them next. So we call this the solid ball model. And here is a beautiful picture of the solid ball model. It is a little circle. It's a ball. It's solid. Okay? And that was what Mr. Dalton was known for. And again, this was science altering. That's why 200 years later I'm still telling you his name. Okay? Mr. William Crookes, with his Crookes cathode ray, he discovered electrons. And I'll show you a little video. It won't be today, but I'll show you a little video that shows how he discovered this based upon magnets and using this beam of light, and the beam would actually deflect away from the light. He said, hey, there has to be something magnetic here, because they knew about poles, positive and negative magnets. So that was Mr. William Crookes. So because we have these electron things, we have to come up with a new model. And J.J. Thomson, another English guy, came up with this model that he called the plum pudding model. Has anybody in this room actually had plum pudding? I didn't think so. So I call it the cookie dough model, because we've all had cookies, I'm assuming. Yeah. Right? Good. I know I certainly have. Okay, the cookie dough model basically is that you've got this ball of stuff. Okay? And that was the positive stuff. And then these little tiny chocolate chips would have been the electrons. So the black stuff would be the positive, and these would be the negatives. So the electrons were kind of just little chocolate chips swimming in this sea of cookie dough. Makes you hungry, doesn't it? Yes. Okay? So again, the textbook calls it the plum pudding model. In this class, I call it the cookie dough model. It just makes more sense, because you all don't know what plum pudding is. Right? Oh, okay, that's good. Fine. It's good. Then came Mr. Rutherford, Ernest Rutherford, excuse me. And his experiment is what we're going to replicate or model with our lab we're going to do. And his model, and this is the craziest thing in the world, okay? And I usually have something to show this. So imagine you took a ball, right? Like this, but I won't actually use this one. And we threw it against the wall. What's going to happen to it? It's going to bounce back, right? Sure, oh sure. Now if I threw it hard enough or fast enough, I could throw it through the wall, right? And you're comfortable that most electrons, if we're machining them or moving them, they're going to go super fast, right? So Mr. Rutherford came up with this experiment. What he did was he put this little thin layer of gold. He called it gold foil. Because gold is this cool metal that you can smash it so small that you can make it just like atoms thin. A very thin layer of gold. Oh yeah. Mm-hmm. It's very malleable. That's a chemistry term. Very malleable. We can bend it, shape it, move it. And he shot at this gold foil these radiation, these positive charged particles. And he was expecting them just to go right through. But instead, they started bouncing back at him. And again, this is what they were expecting. The atoms just to go right through. Because again, there's only a couple of chocolate chips here. It's not going to be much of a difference. But instead, boing, they were bouncing back at him. Remember, he was shooting positive things at it. And we know that two charges that are the same, what happens to them? They repel. So he's like, I'm shooting positives, and positives are bouncing back at me. Man, there must be something positive in this cookie dough that we weren't previously acknowledging. Are you with me? And this was a very small area that was getting these bounce backs, and it was kind of a rounded shape kind of piece to it. And he says, you know what? We're going to call that the nucleus. And inside that nucleus must be these positive pieces. And so we'll call those positive pieces what? Protons. Are you with me? That was Mr. Rutherford. And again, his experiment was so kind of ground-changing that we still talk about it today. You can actually still buy kits to do his experiment with today. I'll show you a video of it. James Chadwick was the guy who discovered a neutron. Remind me, what is a neutron?
No charge.
No charge, but it has mass, which seems weird, but that's just the way it works. Okay, so no charge, but it has the same mass as a proton. We'll talk about those a bit more later. So now we've got these other pieces, protons, neutrons, electrons. We've got to find some new model that holds all of these things together. And so they came up with what's called the planetary model. Mr. Rutherford was a big contributor, as well as a Japanese scientist by the name of Nagaoka, that came up with this planetary model. That here's a nucleus, and that nucleus has protons and neutrons, and then going around it are these electrons in these defined orbits. Are you with me? I have to hurry because we're going to run out of time here. This is not what we believe currently. We believe a slight alteration to that, which is what we call the electron cloud model. We know now that electrons don't stay in these perfectly designed orbits. They actually just are in these specific areas. And it's a probability thing. I'm 99.99% positive the electrons are there, but they could be off in Hawaii someplace. Are you with me? It's about percentages. That's how quantum physics works. It's all about the percentages. Stay with me one moment. One moment. What I'm encouraging you is you need to be comfortable with this progression. There will be a question on your assessment that I'll ask you. Roll me through the history of the atom, talking about the names of the people who were involved, what they did, and how that model changed. Okay? Lab tomorrow. Adios.